Hello, AP Chemistry, and welcome to Chapter 20, where we're going to talk about galvanic and voltaic cells, right? So when we say galvanic and voltaic cells, what does that mean? Right. One thing that it means, oops, one thing that it, one thing that it means is that we are talking about spontaneous cells, right? So reactions that happen on their own without outside intervention, right? Which means that, like your book goes on to talk about, we are talking about going from a high potential energy to a lower potential energy, right? That's why they move spontaneously from one place to another, right? When we talk about a galvanic cell or a voltaic cell, right, it's really no different than what we talked about in the first two sections and what we actually started talking about back in chapter 4, right? So if we think back, we talked about this last time, right? And this is something that, again, like we looked at stuff like this sophomore year, right? Where we have a single displacement reaction, in this case, right, a single displacement, where there's an exchange of electrons, right? Now, all we're doing when we turn it in, when we take it from a standard redox reaction and we turn it into a galvanic cell, what that means is now we're just going to separate our two parts, right? We're going to have a dedicated place where we generate electrons, and then we're going to let those travel through a wire because we need the metal to, conduct the electrons, to something where we can either measure the voltage, or it can be used to power a device like a small fan or a motor, a light bulb, right? Some small device, right? And then those electrons finish their journey over here, where they are then allowed to do the reduction process, right? So same exact reaction, right? We're just setting it up differently so that way we can utilize those electrons on the way to them going to do whatever they were going to do anyway, right? So let's go ahead so this would be a standard classic galvanic cell. So what we're going to do is we're going to talk about all the parts here, and then just know that cells can look very, very different, right? But what matters is that they have all the same required parts. So if we look here, we're divided into two half cells, right? So that's the point again, right? So we have our half reactions we talked about at the beginning, right? And those half reactions then become each half cell, right? So here we have a half reaction, right? And this half reaction would be what kind? Right, this is our oxidation process, and we know it's oxidation because we are producing electrons, so zinc is going from here to a more positive oxidation state, right? So this is our oxidation, which means that electrons are produced, and if we look here, right, electrons are produced, and electrons flow from the oxidation where they are produced to the reduction. So here we have our reduction. So they flow from there to there, okay? And like we said, they're going to flow through a wire, right? And here, in this case, we're using a voltmeter, but again, any small device that can be powered by electrons, right, could be sitting there also. In terms of dividing these up, our anode is where our oxidation occurs, and our cathode is where reduction occurs. There is a little word phrase that people like to use, right? Red cat, and ox, right? And people like to, some people like word things to help them memorize stuff, right? As in reduction happens at the cathode, oxidation happens at the anode, okay? Anode is our negative end, so if we were going to label it, anode would be the negative end, which makes sense, right? Because if we just think about it reasonably, that's where we are producing electrons, right? Electrons come from there, so that would be our negative end, okay? And they flow toward the positive end, right? Which makes sense again. Electrons are negatively charged, and they're going to flow towards something that is positive, okay? And so here we have our electrode, right? Our zinc electrode, our copper electrode, and here is where we get the first part of our reaction, right? So zinc basically becomes oxidized, right? And then those electrons travel up my zinc electrode through the wire into the copper electrode, right? And then here we get our reduction process. Like your book does talk about, these electrodes don't have to be things that participate in the reaction. They are often inert electrodes, things like platinum, things like carbon, which means that if they are inert and they do not participate, their masses do not change over time, right? I mean, actually, let me not say that, because sometimes if we get plating on it, then yes, the mass will change. But often we do use inert electrons that do not participate, right? Here, right, they are participating, right? As in, like, we have zinc solid and my zinc and copper and copper. And then, finally, last important part, we have our salt bridge. So if we think about what's happening over here, we are doing what? right? We are producing zinc cations, which means that in order to maintain neutrality in my solution, right, we are going to get the migration of anodes in this anions in this direction. Here we are consuming cations, so cations will migrate in that direction. Here, again, we have an outside salt bridge, right, where we have an inert solution, right? So here, note that neither sodium nor nitrate are part of our overall reaction. So that would be an inert salt bridge, right, where we have something that doesn't participate but contains ions that can migrate in either direction, right? If we take a look at this next one, right, here we have the exact same thing, right? We have electrodes, we have the flow of electrons, we have something that measures our flow of electrons or shows us that electrons are flowing, right? We have our half cells, but instead of a salt bridge that contains an inert and inert ionic solution, here we just have a porous barrier, where porous for our purposes is going to mean ions can go through, water cannot, okay? Ions can go through, but water cannot, which means that here we already have a solution of ions, right? Here we have a solution of ions. So as we produce cations on one side and consume cations on the other, right, then we can get the migration of the necessary ions through the porous barrier. Yeah, makes sense? Here we have table 20.1 with our standard reduction potentials. So again, these are reduction potentials, right? So always, always reduction, right? This will not always be labeled with the sub RED, right? But you'll know their reduction reactions. Why? Right, because they will all have electrons on the reactant side, right? Which means that whatever we're starting with is a higher oxidation state than what we're ending with, right? So you'll know, even if it doesn't say that, okay? So just going over a couple of points here. Here we have a positive E0 value, which means, right, that this reaction is favorable as written. Here we have a negative E0 value, which would mean this is unfavorable as written. All right. So if we look over here, what that means, right, so that means that fluorine gas is readily reduced, right, spontaneously on its own without outside intervention, readily reduces to fluoride ions, which makes sense. Fluoride ions have a full valence. That makes sense based on everything we've talked about this school year, right? Which also means if fluorine is readily reduced, meaning it readily takes on electrons, what does that mean about it? Right. It means that it is a good oxidizing agent. I missed a lot of letters in there. Oxidizing agent. Yes, good oxidizing agent. All right. Yeah, I forgot what I was going to say. All right. If we look down here at negative 2.71, right, meaning unfavorable, not going to happen, we have sodium ions, right? Aqueous sodium ions turning into sodium solid. Is that something that seems reasonable? Right. No, right? Sodium is always found as ions in all of nature, right? Which makes sense because sodium ion is where we have the full valence. Whereas here for sodium solid, that's not true, right? It's got that one valence electron, makes it highly reactive, etc., etc., which makes sense that this reaction does not go as written, right? Because sodium does not readily take on electrons, okay? Now, if we're going to look at this in the opposite direction, what that does mean, though, is that sodium solid readily gives away electrons, yes? If sodium solid readily gives away electrons, what does that mean? Right, that means that this is a good reducing agent. Yes, does that make sense? Okay, and then here is your standard hydrogen electrode, right, which is neither, it's not favorable in either direction, right, and that's the standard by which everybody else's reaction E0 value is measured, right, which goes back to that figure in your book, right, where we have our She compared to some other reaction, right, and that's basically how we're setting our values based on this one right here, okay. All right, and so then that's how so we would use this table to figure out if a reaction is going to happen or not, and how to pick the reaction that's going to happen, okay? And this is sort of just a summary of all of that. Make sure you go over this figure, right? And make sure it makes sense. Make sure you can look at this figure and put all those pieces together.
So here's a practice problem where we are going to figure out what's happening in a galvanic cell and answer two specific questions. So what half reaction occurs at the anode? which means we need to figure out what the reduction reaction is and what the oxidation reaction is, so we can put the whole thing together, because we're also going to answer what is the standard cell potential. Okay, so first things first is we need to get a visual on what's happening in the cell, right? Sometimes you can just do that in your head, right? Some people are really great with just visualizing, right? Some not so much, right? And if you know that is something that's hard for you, right, just doodle the cell and that will be helpful to you, right? So it says that one half cell is composed of cobalt and cobalt plus 2, right? So that means we have one half cell that is composed of, I have some cobalt plus 2 ions, and I have some solid cobalt, right? That's what's in one half cell. The other half cell is composed of silver chloride and silver, right? So I know that I have, and note that it says silver chloride. What do we know about silver chloride? Right, it is insoluble, right? It is not something that's aqueous, right? And silver is my other component, right? So I know that there is going to be some silver solid here, right? And it turns out that the way these cells work, right, are that there is also an AgCl coating on this cell, right? And there are just chloride ions floating around in here, usually potassium chloride ions. Now, visualizing an AgCl Ag half cell might be beyond your abilities, right? But if it were, for example, an Ag plus Ag cell, I think that would be easier for you to sort of visualize, right? But anyway, we've doodled out our cell, and we have what we need. Obviously, there would be a wire, there would be either a voltmeter or a device here that it could power, and what's the last thing it would need? Right, we would have a salt bridge, which would connect these two, so they could have an exchange of ions, okay? All right, so we have the visual for our cell. Now, the tough part is to figure out which reaction is the oxidation and which reaction is the reduction. So here, I've just transferred some of the things from the appendix in your textbook that have species that are relevant, right? Because if I know my only species are cobalt and cobalt plus 2, silver and silver chloride, right, I'm only going to use reactions that contain those species, right? That's all we have. So here are my three options. And what do I know? If I know that it's a voltaic cell, what's a big clue that I have that will help? Right, I know that my overall E naught value must be positive, right? That's something that must be true for my cell. So let's go ahead and figure out what my oxidation and my reduction reactions are going to be, okay? Let's do reduction first, because that's the one I think that's easiest, right? Because we're going to use these reactions as written, because again, they're always, if we look here, these are always going to be written as reductions, right? And these are my E reduction values, okay? And we know it's reductions again because electrons are on the reactant side. So, looking at my choices, right, we can reduce cobalt for a negative 2.277. We can reduce silver ions, or we can reduce silver chloride, okay? Now, what's the problem here? Right. While that might seem tempting, right, we don't actually have any silver ions. Yes, does that make sense? We have silver chloride, according to our cell description, right, and we have silver solid. We don't have any silver ions, right? We might produce some, right, or some could be, so they could be present later, perhaps, right? But the point is there is none right now, which means that's not an option for the reduction, which means that these are the only two options for reduction. And if we look, the silver chloride is the only favorable one, right? So that's going to be our reduction reaction. So Ag solid plus electron gives us Ag solid plus chloride ion aqueous, and that's got an E naught value of 0.222 volts. Okay, now we need to figure out my oxidation. So if I've already used this one and this is not an option, that means, right, ding, 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 that must be my oxidation reaction. Now, in order for that to be my oxidation, what am I going to have to do to it? Right, we're going to flip it the other direction, right? So I'm going to have cobalt solid turns into cobalt 2 plus 2 electrons with an E naught value of now, right, 0.277, right, because we're going to flip that when we flip the equation, right? If I wanted to come up with a full summary equation, do be mindful we would have to do what? Right, we would have to take this whole thing and multiply it by 2, Would I multiply my E value by 2? Right. No, because E is a intensive property, just like density, right? If the mass of a sample goes up, its volume goes up, but the density does not change, right? Where if you think about a volt is a joule per coulomb, right? If I have more coulombs, right? More electrons means more coulombs, right? I'm going to have more energy, joules, come out of my cell, but the ratio of that, which is volts, will stay the same, okay? All right, so then going back to my question, which happens at the anode? Right, this happens at the anode, which makes this my anode. And my overall cell potential would be the sum of these things, right, which would be 0.499 volts as my overall cell potential. Yes? Make sense? All right, so when we're looking at a cell and we're trying to answer questions like which is the anode or what's the cell potential, right? Step one is always, right? What's present, right? And then narrow down the reactions that are plausible, and then figure out what's going to work in the context of your cell. All right. All right. Thanks for listening. Be good, and I'll see you soon. Bye.